So two important announcements that if you've looked at the syllabus. So I have yet to post a quiz. So don't forget, we're going to have roughly 15 quizzes this term. They're not going to be scary things. They're going to be, these quizzes will be, hey, you have a window of a couple days, pick your favorite time, you go on, maybe answer a couple questions. I may ask you to watch a video. I may ask you to read something like that. They're not going to be difficult. They're 5 points each. So keep that in mind. And then the other thing is, for those interested, I know we talked about this earlier in the week, I still didn't post my math lab yet. So I'm sorry if you've been patiently waiting. I apologize. But I had no power last night due to weather, and this morning, I ain't gonna lie, I completely forgot. So there's that. All right, so what we've been talking about, and I thought I admitted you, Carly. Sorry, Carly, I thought that you were, it had admitted you. It's like, I'm gonna get rid of this waiting room, I think. Okay, so what we've been talking about is volume. So the first thing we have to point out is in homework 2, there's a typo. So let's point that out now. So I want to share this. Hopefully you guys are all seeing our Canvas page right now. And if you go to the assignments and you click on homework set 2, what you'll notice is, what is it, problem 4 or 3 or 4? Problem 4. So problem 4, there's a slight typo. And so we need to pick an interval. So here's what we'll do. We'll make it very easy to figure out. So, so there's a typo on number 4. I forgot to give you an interval. So why don't we use, whoa, what's happening here? My pen went AWOL. So why don't we use, say, 1,4? That should make the math easy. 1,4. Okay, so if we go back to the homework for a second, we've given you, we've talked about, at least if you're going off of what we've done in class to this point, you guys should be capable of doing problems 1 through 5, 6, 7, 8. The place we haven't quite covered yet are problems 9 and beyond, all right? So does anybody have a question about 1 through 8 before we go on any further? Does anybody here? 7. So the first person to ask is problem 7. So let us look what 7 is. So we have a curve, square root of x minus 1, and we are going to revolve it around the y-axis. Let's get the volume of the solid. Okay. So square root of x minus 1, 1 comma 5. So this is number 7. So the curve we're taking is y equals the square root of x minus 1 on the interval 1 comma 5. So let's draw what this looks like. So we're only interested in what's happening between 1 and 5. And if you're not quite sure what to do here, well, you can always go to Desmos, but let's just assume you can reason it without Desmos. What does this guy look like? Well, when you plug in 1, it spits out 0. And when you plug in 5, it's going to spit out 2. So it's going to go through, the graph's going to look like this. And another way to think about this is just a square root graph shifted to the right 1. And so what the region that we're interested in is this region. And let me emphasize again that this is the point 5, 2, although that's the only thing that matters really is the 5. Okay, so what we want to do is we want to revolve this creature about the y-axis. So we're going to rotate it about y. So again, you're going to need to have a fair amount of, what makes these problems difficult to sketch is you have to have a fair amount of imagination. You have to really, really think outside the box as opposed to plugging and chugging. So what I'm going to do is I'm going to, the way I like to do this is I like to think about my shape. It looks something like this. And I like to pick a sort of like a vertical line and ask myself, how does this vertical line, this sort of little rectangle, what happens when I rotate it around y? And what I end up getting is I end up getting some shape like this. Now again, I'm trying to get, this is not as easy to do as you would think. And so it's going to be sort of like a cylinder. And so what one way to think about sort of how we might do this is you're not going to see this and you're not going to see this. These are going to be inside. So you could think of sort of these as dotted lines because you're not going to see them. And you're going to have sort of like a circular, a little cylinder inside of here. And even these creatures right here should really be dotted or ignored. And then what you will see is you'll see sort of this piece. So you can maybe say this is there. And then this comes back around. So the way I would encourage you to think about maybe how this guy sort of looks. You guys are a little younger, but back in the day, you'd get like a grocery store or the mall. They used to have these big things. They look like a funnel. And you'd like drop a quarter and it'd roll all the way around. That's in my head, that's sort of what I think this thing looks like. Let's see if we can get a picture of one of those to help illustrate. That's always fun when we try to do that. How did I get a funnel? Because this curved part right here, when I all we're moving is the red region around. So first off, there's a hole in the middle. There's not going to be anything here. So the way out, again, you have to have an imagination. It's really difficult for one person to describe it to someone else. Really what it takes is it takes you to have whatever time it's going to take for you. For some of us, we get it. We see it right away. Others, it takes some time. So I said, imagine, a good thing to do is imagine you have some strip right here that I'm highlighting in blue, and ask yourself, if this strip, think about this pen representing this strip. And so my hand will be the y-axis. What happens to this strip when I rotate it around the y-axis? It just comes out and around, back in, and then through and behind.
I don't know, I understand how you draw the graphs. It's just the shapes that just don't.
Well, that's the thing. It's not easy to do. I mean, we're trying to draw a three-dimensional object in a two-dimensional world. That's actually impossible to do unless you're a really, really good artist, but we're not really, really good artists. This is very difficult to try to imagine. But again, let me repeat this because I think it's important. Here's the y-axis. I'm taking that blue strip. You see the blue strip, and I'm imagining what this one piece does. So if my hand's the y-axis, and This is the x-axis. This moves out and back, and then it comes around and through. So it creates a disk. A good visual of what it creates, Josh, is something like this. You guys get these wristbands. If I think about it, that's what it's a visual of what it creates. It creates this wristband. So imagine I took 40 of those blue strips right there, and I rotated them around. I would be approximating that shape with 40 of these things, sort of all cascaded on each other. Some would be higher, some would be thinner. The closer they are to 1, the thinner they would be. The closer they are to 5, the taller they would be. So again, there's nothing easy about this. What I was going to show you, and I don't know if this will be useful or not, let's see if I can get it to work. Coin funnel. So the coin funnel things in malls. I don't know. That's what, see if we can, I know it's going to give me, yeah, something like this. One of these, I imagine it looks, there we go. See if I get a better image. Yeah, this is what I sort of imagine it looks like. Something like this. You used to, does anybody remember these things? You like drop a coin in and it rolls around, and then it goes all the way down into, well, maybe that's another name for it. Coin wishing well funnel. I don't know. I'm just trying to figure. I'm trying to get a better picture. Here's this one. Here we go. The way I'm imagining the solid is like this black thing inside. That's how I'm imagining it. Again, I'm using the word imagining. You might be imagining it a different way. But that's the way I'm thinking about it. I'm thinking about this as this is a hole. Okay, nonetheless, we can compute the volume. Even without drawing this, we could have computed the volume. The volume is the following. Since we rotated around y, what I told you yesterday is that you should often try the shell method first. And so the volume here is going to be the integral 1 to 5, 2 pi x times the function, which is x minus 1 dx. Now, this integral tends to give people problems, but it doesn't have to. There's a couple ways you might evaluate it. First off, I'm going to pull the 2 pi out. So anytime you have an integral that looks like this, one sort of idea to try is to use a substitution. So what I'm going to do is I'm going to set, say, y equal to x minus 1. And then dy is equal to dx. So the way I'm going to proceed, and you can proceed in another way as long as it's legal, is the first thing I have to do is change my bounds. My bounds now go from 0 to 4. And what I'm left with is, watch what I'm going to write. I'm going to write y plus 1 times the square root of y, dy. So this is sort of a step that some students miss. And how am I getting this? Well, if I look at this expression right here, I can rewrite this. This is the same thing as y plus 1 equals x. And so what I'm doing is I'm replacing x with y plus 1. And then I'm replacing x minus 1 with y. And what that does is that takes the square root term that had 2 things inside of it, and now there's just 1 thing inside. And now algebraically, this is a lot easier to handle. Because algebraically, if I just remember how to distribute properly in my exponent laws, this integral becomes y to the 3/2 plus y to the 1/2 dy. So why are the bounds 0 and 4? Well, that comes from this expression right here. So we're changing our variable from x to y. So if you look at this expression here, what do you have? Well, when x is 1, y equals 1 minus 1, which is 0. And then when x is 5, y equals 5 minus 1, which of course is 4. Does that make sense? Remember that's the way I prefer to do it. I always change my bounds when I do a substitution. You're not obligated to do it that way, but I encourage that. And then the other thing that often students will kind of forget is this distributive thing. So this is, I'm rewriting the square root as 1/2 power. So when I distribute it, I get this. And then of course, when you integrate this, what does this become? Well, 3/2 plus 1 is 5/2. So this becomes 2/5 y to the 5/2 plus 2/3 y to the 3/2. And we're evaluating from 0 to 4. So when you plug in 0, everything's going to disappear, right? So we're not worried about the 0 part. We are worried about the 4 part. And even though this looks scary, it doesn't have to be, because since the bound is 4, 5/2 just means take the square root of 4, which is 2, and then raise it to the 5th. And then 3/2 says take the square root of 4, which is 2, and then raise it to the 3rd. So this becomes 32. So if we want to be sort of cute, this becomes 2/5 times 32 plus 2/3 times 8. So make sure that that makes sense to you. If you have a question about that, again, you can use a calculator if you want. I got to be honest, I think you should only use calculators at the end, but I'm old school. And so you might think, oh, Grady, shut up. But I don't care what you do need to have the exact answer before you do anything else. So I believe if we've done this correctly, this should equal 5/44 pi over 15. I believe. So does anybody have a question about this particular problem? Yes. There's not two functions. There's only one function. No. But remember, see, that this is where it comes back to. So the question was, why didn't I subtract anything? Well, let me explain it this way. You only subtract when the bottom of your region is another function. The bottom of our region is not another function. Look, the bottom of our region, no matter where I draw that blue rectangle, the top is always f of x, the bottom is always 0. So I'm not subtracting anything off. Now, perhaps you're thinking about if you were to draw a horizontal blue line, then you would have to do it differently. Now, if you did it that way, that's a train wreck. That algebra is a mess. That's why I'm saying anytime it's rotated around y, use the shell method. Does that make sense? I don't know. Does that make sense? I don't know. I don't mean to just, blow you off. But that's the way I would encourage you to think about it. Remember that one of the key things, and for those of you who go on and take Calculus 3, this is important too. One of the key things is to understand your integration variable is dx when your slices are vertical. Your integration variable would be dy when your slices are horizontal. So that's something to consider too. So think about your slices. When you're doing a shell method, your slices are vertical. When you're doing the disk method, they are going to be vertical. The only time any slice is horizontal is if you're trying to do it with the opposite variable. So that's a subtlety, but it's an important one. All right, any other questions about this problem? All right, so someone else, what problems of vulgar you said, what, 4, 5b, and 8. Okay, so let's look at 4. Actually, let me pull it up here. I was trying to pull it up so I don't have to. So this would be what? Number 4. Is this the one that's like an algebraic nightmare? Oh yeah, so 4, I mentioned earlier, 4, you can't, once you give you a bound, it makes sense. So for 4, what did we say for 4 to use? 1 to 4, yeah. So 4 is, if you look at number 4, so 4 is actually a pretty easy one, so I'll leave that to you, but I'll get you started. So you have y equals 1/4 x on 1 comma 4. So what does that look like? That looks like, I mean, that is just a line of slope 1/4. So if I wanted to graph that, it looks like this. So we're going to have to make it to scale. So if I plug in, say, 1, then this spits out 1/4. If I plug in 4, then it spits out 1. And so the region that you're interested in is this region. So when you rotate this creature about the x-axis, oh, did I say y? Oh yeah, y, okay. So this is very similar to the other shape. It's just not curved. It's sort of like a cone drilled out of a cylinder. So when you rotate this guy about y, my advice would be to use the shell method. Yeah, I didn't. So Zafalgar, you joined in a little late. That's on the first slide. There's a typo in number 4. I didn't give you an integral. So now I'm saying let's use 1 to 4. So when you rotate this thing, what is it going to look like? Well, again, it's like a cylinder with a hole drilled in the bottom and then a cone drilled out in the top. So I would encourage you to think of it like this. So again, it's really hard to draw this. So the way I'd ask you to imagine this is a cone hollowed out of, and not just a cone without a top, hollowed out of a cylinder. That's the way I would encourage you to imagine this shape. And then I'll let you do the integral, but the integral is going to be straightforward. By the shell method, it's just going to be integral 1 to 4, 2 pi x times 1/4 x dx. So that's a very elementary integral you guys should be able to do. And I don't want to steal all the fun. Okay, now does anybody have any question about this before we do 8? 8 is a fiasco. Well, 8A is not that bad. 8B is Ooh. All right, so for 8, look, you're given 2 curves. Now, I'm not suggesting you should know how to graph these without a calculator, but you could easily reason what the region looks like with just a little knowledge of algebra. Because the first curve I give you is a parabola that's open down. How do I know it's open down? I know it's open down because it's a minus sign in front. And then the second one has to be opened up for the same reason. We learned that polynomials leading coefficient positive means up, negative means down. Now, at the same time, you could go to Desmos and verify that for yourself. The other thing to note is you can easily see where they intersect by solving. So if I go, and when I say easily, please don't take offense to that. But what I'm saying is the math is straightforward. It's math that you learned a long time ago. So where do they intersect? Well, they intersect where negative x squared plus 2x plus 2 equals 2x squared minus 4x plus 2. Well, this is not a hard equation to solve. I will bring everything to the right-hand side because that way my leading coefficient becomes 3x squared, then minus 6x, and then the 2's cancel. So that is the same as 3x times x minus 2. And so I clearly get solutions for this is x equals 0 and x equals 2. So now I know what the region looks like. I have a great idea of what it looks like. Again, I don't need it exact. I just need a sketch. So if anybody has a question about that, please let me know. So again, let me just illustrate that. Just doing that little bit of algebra, I know right away that both curves intersect at 0 and then they intersect at 2. Now the question is, where do they intersect at? Well, yeah. This is number 8. Oh, wait. Am I doing the right? Yeah, no, this is, yeah, I'm sorry. I wrote that down wrong. This is 5. Why'd I write 8? This is question 5. My apologies. Wait, we're having a hell of a go at it today. This is 5. I said 5 and I wrote 8, maybe? I don't know. I should retire. So the only thing I have to do now is what's the height at these points? Well, if you plug in 0, both of them spit out 2, so you have that going for you, so they hit this point. And then if you plug in 2, they both spit out 2. So I can reason right away. All I need to know now, I don't need to know anything. I know what the region looks like. It looks like this. I don't care what the rest of the graph looks like. I know the top looks like this. And then I know the bottom has to look like this. So again, this is the red curve. And then the blue one is the top one. And so the region that is of interest now is what I'm going to shade in pink. Like a little fish. Although it's very symmetric. If you graph this, you'd realize it's symmetric. So I'm not going to steal all the fun from you. So the area part, the area is just the integral of the top minus the bottom. So that's 0 to 2 of blue minus red dx, which if you do this properly would be minus 3x squared plus 6x dx. You should verify that for yourself, and then I'll let you do that integral. It's not a challenging one. That is a baby integral. Does anybody have a question about this? That's the area, blue minus red. Top minus bottom. And you should also convince yourself that that's the only reasonable region that is enclosed by those two curves. Any other region is not bounded by those two curves. In fact, every other region that you see on the plane, there's 4 of them, left, underneath, top, and right. Those are all unbounded regions. Okay, so if that's the area, so that's part A. Now the fun part, and I ain't doing it for you either, you guys can suffer through the detriment of it. What's the volume? Well, the volume, when you rotate this around, you're going to get like a donut. So when you rotate this about the x-axis, what it's going to yield, and again, you're going to have to really use your imagination, something like a donut-like shape or solid. So you would imagine it's going to look something like a donut. That makes it look bad. Yeah.
When exactly was the point that was touching 0, 1, 0?
Oh yeah, it might touch 0. That's fine. That doesn't affect anything. Well, that actually does. It will make your donut a little. Okay, so I see what you're saying. So you're saying when you graphed it, the red comes all the way down. Yeah, that's fine, but that doesn't matter. We're just sketching it, but I get what you're saying. So the point was being made that actually the red curve should touch the x-axis. But again, we're just sketching it. So make sure you understand that. We just want to get an idea what the region looks like. So you're not wrong, but this is just a sketch. But that's a very good thing to understand, because when you do that, if you understand that, then this shape has a very sort of interesting, it creates a very interesting solid. So you're going to have this inside piece that's going to look sort of like this. So a good way for you to think about what this thing's going to look like is sort of like a hole, maybe. So let me give you a better visual than what I can draw. A Ford Taurus. But it's sort of like, so the mathematical word for like a donut is this torus. And the one we're thinking about, if you can see it, is the one where they're going to zoom in on it, where it's almost like the center's touching. Does that make sense? So that's sort of what we're generating. By the way, if you're interested, there's a branch of math that people study that has applications everywhere called topology. And it's the study of things like that, knots and all kinds of cool surfaces and curves. It's pretty interesting. All right, so let's go back to this problem. So, but anyhow, nonetheless, no matter whether you visualize it or not, the volume formula is the same. The volume is going to be the integral from 0 to 2. Now, this is where you subtract out, and this is going to be brutal. You have to take the top. What's the top? The top is, what was it? I forget already. It was blue. So the top is blue squared minus pi times the bottom, which is red, it's quantity squared. And then this becomes, pull pi out, integral 0 to 2 of this thing, minus x squared plus 2x plus 2, quantity squared, minus pi times this integral. And the thing to be very well aware of here is this problem is an algebraic nightmare. And then once you do the algebraic nightmare, you get easy integrals, and then that equals what? Well, I'll let that be up to you. If you don't want to do the algebra by hand, don't. You know, verify it with a Wolfram or something. But you should suffer through the calculation. It gives you an appreciation for things. I mean, that is a problem that you would have done in algebra class where you have a polynomial of 3 terms and you have to square it. I mean, you have to FOIL it, not even FOIL, I'm sorry, distribute, then distribute. It's a mess. You're going to get a polynomial of degree 4. Right? Because you're going to have x squared times x squared is x to the 4th. And then there's going to be all those terms. One way to verify that you did it correct, if we go back here, we can go to, say, Wolfram. And to get Wolfram to do it, the correct command is do expand. And then you could just type in, what do you want it to expand? You want it to do minus x squared, say plus 2x plus 2, quantity squared. And it'll do the algebra for you. Although, again, I recommend you do the algebra. See, polynomial of degree 4. Suffer through it. Gives you an appreciation and thanks all the nerds that made this possible for you. Shake your head no. The nerds who make this possible get paid very well. They get to work from home. They get to enjoy life. By the way, you can even tell Wolfram to do the problem for you. Well, I don't think it will. It might do the area part. Let's see. Let's see if it'll do it. Determine the area bounded by y equals minus x. It might be able to do this. This is pretty cool if it does. I don't know if it can handle ones this complicated, though. We'll find out. This will be so cool if it doesn't. We could just, might as well just give up life. Nah, it doesn't know how to do it. But it can do some area problems if they're simple enough. I don't know about volume, though. Although there's probably another web page that'll do it for you. Yeah, no, it's still not going to know, I don't think. We'll find out, Alex. Usually if it knows, oh, no, it does know. Ha! Just like that, it solved the problem for it. Look, it graphed it and everything. Look at that. What a time to be alive. And if you pay them, they'll show you the steps. Does anybody have a question about this? So here's the thing, and a lot of people would say, why would you show students that this can be done? Well, look, I don't care what you do. You get an A in this class by taking all the answers off the internet. That does you no good when you're in a job interview. Because when they ask you to do something, you'll be like, huh? Like, that's the most, you know, if we can. No, it ain't allowed. You got to show the work. Fools. I mean, look, you're not going to really have problems like this on an exam. I mean, I'm not an idiot. I'm not going to give you a problem that you can type into a machine and gives you the answer, right? But no, if I can be, when I give you the exams, there's no, they're going to be take-home exams, so you can use any resource you want. But remember, you're going to have to explain details of your calculations. That's what I'm saying, Ethan. If you upgrade the Pro and copy the work, that's fine. And then so let me give you an example of what happens. This is a very big problem in for computer science and programmers. Is the way people learn to code is they learn to code by looking at other people's code. That's common. I learn by sharing stuff, and you learn by sharing with me. And the biggest mistake that the students have is, yeah, I mean, but it's not plagiarism if you source yourself, Emily. So if you source yourself, it's not plagiarism. So someone was asking it, if we allowed to use this on an exam, and I would never tell you not to use Wolfram. It's just the problems on the exam are going to be a little more involved than just computing the area. Right? And what you need to think about is what's more and more common in job interviews, particularly in the tech world, is what can you do? So for instance, computer science majors will have a job interview, and the very first thing they'll do is they'll put you on like a Zoom call or something. And then they'll ask you right in front to do something. You know, oh, you should know this. This is elementary. Can you do it? And what happens is oftentimes students can't, and it's not because they're nervous, and it's not because they're not capable. It's because you guys make the biggest mistake that you can make. And here's what it is. You guys live in one of the greatest times to be a student, to want to be learning. Now, we can argue about the rest of the world right now. That's not my point. My point is you live in one of the greatest times to learn things. You have no other person on history has lived in a time where everything that the human brain knows you can find in a second. Right? There's not a damn thing that humans know that you can't learn just by Googling it. And yet what you numbskulls do, which is so fascinating, is all you do is copy the shit down and turn it in. You don't even try to learn it. Think about that. You are wasting it. All these resources that are mostly free to you guys, and you don't even take the time to learn it. And so the difference is between that, and I don't necessarily calling you out as students in this class or students at LaRoche. I'm saying in general, that has been my experience, and that is the experience of people who hire people. I've shared this with you before. I have friends who are in business where they hire graduates, and that is the biggest complaint, is that you guys don't know how to do things. And the reason you don't is because all you do is copy shit off the internet, right? That's all you do. And the difference, and that's not that there's nothing wrong about copying stuff off the internet. The huge mistake is the huge mistake is that you don't actually use that resource to learn it. Think about how much easier it is to learn if you already have the answer. And then all you have to do is figure out how they got the answer. I mean, that'll, and it's not just in math. I mean, math, again, this stuff is, no, Mohammed, look, we'll get to how testing is going to work in a second, or not when the time comes. But it's not about, for me, it's more about how you communicate things. It's about how you express things. This is not going to be a problem on your test. I'm not a fool. If I give you a take-home test, I'm not going to ask you to compute the area of something that you can plug into a computer. I mean, I'm not an idiot, right? I might give you one as a freebie, but most of the problems are going to be a little more nuanced. But again, I can't emphasize this enough. And I'm not saying this because I'm like the professor who wants you to learn it. I'm saying this is, I'm trying to get you to understand what the world is wants when you go out there and look for a job. They want people who are capable of learning and doing things. And you're going to be competing with a lot of other people. And guess what? There's lots of people all over. I mean, look, I'm not a fool. I know how, you know how many people pay someone else to do their math homework? That's a very common thing. Hell, most of you, there's a whole business, there's a whole group of people in other countries that get paid to do everybody's homework, right? You go online, you pay them, they do your homework for you. Right? There's databases of all these papers that, you know, someone somewhere else writes for Josh and writes for Reagan and writes for me. I mean, that's, we understand that this is how the world works. And see, the thing is by you just copying it to get a grade, you're not pulling a fast one on anyone. Because at the end of the day, I know people say grades mean anything. If you ain't going to medical school, no one gives a damn what your grades are. I'm not going to lie to you. They just don't. No one cares if you have a 3.8. No one cares. What can you do for them? Now, if you want to go to medical school, you need good grades because everybody else has good grades. You want to get a degree in engineering, you need certain grades because they kick you out if you don't. Is it fair? No, but that's how they roll. But for the rest of us who are just graduating, if you have skills and you have a 2.6, you're going to get a job over someone who has a 3.8 if they just sit there like, huh? And if they don't show their skills. You got to show your skills. And coming full circle back to this, it ain't about calculus. And by the way, you might be saying, he keeps saying ain't. How does he get a job? Fool, because I know in the job interview how to act. I can say ain't in front of you. You think if I'm in front of the president of LaRoche, I say ain't? I might actually. She likes me. I think she likes me. I'm not positive. Do you guys know the president's name? Sister Candace. You should know these things. She's also a PhD. You should also know that. But anyhow, coming full circle. Look, use these resources. I mean, you guys live in an amazing time. Everything the world knows is on this phone. Everything, every piece of knowledge that the mankind, womankind has is on this phone. Well, not on this phone technically, but the phone can find it. You got to use that. I mean, years ago, the only place to get knowledge was to go to a library. That's the only place to get knowledge. And if you lived in a wealthy area, you had a nicer library than the poor area. Well, that don't matter anymore. Everybody, internet's for all. You can all make it rich on here too. So anyhow, I don't mean to beat the dead horse, but I do want you to know that things like Wolfram exist. And I do want you to use these resources. But I don't want you to just copy it down to get the answer. I want you to learn from them. Think about how much easier it is to learn calculus now than it was 10 years ago. I mean, you could do a calculation by hand and then verify it automatically. And then if you get it wrong, you could say, where did I make my mistake? Just by looking at someone else's solution. In a lot of ways, that makes me obsolete. I long for the days when I don't have to teach calculus. No, I actually like teaching calculus. I think it's a cool subject. All right, anyhow, listen, I'm done preaching. I'm not saying any of that to be mean. That's not my point. I'm trying to encourage you to learn. So Muhammad's asking, you should lose. Yeah, I mean, look, I can't, I'll never know how you're using it. I don't know if you're using it to learn or just to copy. I am encouraging you to use any resource as a learning tool, not just math software. Does that make sense? So I'll explain what that means when we get closer to an exam. And when I grade your homework, I'll tell you when I think you need to explain things and when when you're cool just using a calculator. Look, times change. Times definitely changed. Years ago, people would have not wanted you to use a calculator. You know, if you're learning arithmetic, we want you to learn arithmetic. If you know arithmetic, then use a calculator. And so when you're learning calculus, we want you to show that you understand calculus, even though we know that an engineer who uses calculus perhaps every day is using software. So anyhow, we'll talk more about this. And I don't mean that to rag on you guys. I'm not suggesting that it's like cheating or you're cheating. It could be, some people would consider stuff like that cheating. And I'll explain what I think is cheating later, but it's not important right now. It's only important when we get to our exam. Does that make sense? All right, listen, it's time for us to go because it's the Roni rolls. Thank you very much. If you guys have any questions, please email me. Oh, yeah, someone asked about problem 10. Real quick, let me just explain. Oh, you said 8 too, Zavulgar. So, okay, why are people freaking out about 8? 8, when you square it, it's easy. So let me say this real quick. 8 and 10 people wanted to ask. So if you want to jump off, feel free. If you want to leave, I'm not mad, but if you want a little more help. So number 8 is, this is actually sort of you can cheat, not cheat, but there's a shortcut to 8. 8 is, if you graph it, 4 minus x squared is a semicircle of radius 2. That's the curve square root 4 minus x squared. And so what you're doing is rotating this about the x-axis. So you get a sphere. So you can either cheat and take the area of a sphere, or excuse me, the volume of a sphere, but the other way to do it is to just compute the integral. Volume is integral -2 to 2 of pi times this guy squared, which of course, if you pull out the pi, this is -2 to 2, and then all you're left to integrate is this. The square root and the square cancel. So that's how you do 8, the calculus way. And I would tell you not just to use the volume of a sphere formula, because that formula comes from calculus. You should get 4/3 pi times the radius squared. Does that make sense for 8? And then problem 10, don't worry about 10 right now. Or actually, don't worry about 9 on, because we didn't talk about them yet. So when did I say this was due? We'll probably push it back. Yeah, so this will not be due August 31st, okay? I'll fix that. Does that make sense for everybody? So again, let me just say that real quick. So homework 2 is now due. Let Let me change the date while we're on here. This is what I like to do. Homework set 2. I'm on here to update immediately. Right now, it's August 31st. We don't want that. Let's say we need at least Tuesday, so we'll make it due Thursday. That way you have 2 classes to ask questions if you have any. There you go. So now due next Thursday. Do we have, is there classes Monday? Is it Labor Day? When's Labor Day? Does anybody know? Anyhow, you guys don't care. Listen, guys, thank you very much. I'm going to shut her down. If you guys have any questions, email me. Have a good weekend, and thank you very much. Be safe, guys.